not from time to time, so I know I'm not losing people. And so I'll tell you about some work that we finished with Carlos and Vasco, and maybe about some work that we are doing, which is kind of follow-up work with Alexandre on this multi-point bootstrap. Okay, so my understanding is that we have 40 minutes, then a break, and then 20 more minutes, right?
Yeah.
Very good. So let me first describe what computation we are going to do. So that I will do in this page. And then in the next one, I will say a few words about why we are doing this computation. But just to set the stage, let me then be very precise about what we are doing. So what we are studying is we consider a non-abelian gauge theory at large N. Of course, one is n equals 4 super Young-Mills, and part of this discussion will apply to n equals 4 super Young-Mills only, and part will be very general. And then, in this non-abelian gauge theory, we will consider 6, for example, point correlation function. More precisely, we do n point where n is bigger than 4. But let's, for concreteness, say 6. Okay? So we take a 6-point correlation function. So this is an insertion point, and say here we put some gauge invariant operator, say trace of phi I square. This would be the lightest operator in my non-abelian gauge theory. So this would be the lightest gauge invariant operator. Then, okay, it's a 6-point function, so there are 6 points. Six. Okay. They are at some positions. And then what we are going to study is the limits when this insertion, these positions, go to the cusps of a null polygon. So this would be, there would be some null polygon. For example, in this case, it would be a null hexagon. And so all points become consecutively null separated. So we take this limit where all points approach the cusps of a null polygon. Okay. And then we consider the limit of this correlation function, this 6-point function. And the goal is to study this object. This object is in this limit. It will be a function of what? Of the 't coupling in n equals 4. We are at large n in the planar limit. And of the geometry of this null polygon. And I will describe what this geometry is and how we obtain it. And the idea is that this function, we will learn about this function on the one hand, using ideas that are called bootstrap ideas, that are a priori unrelated to integrability. And in the case of n equals 4, we can also learn about this function, of course, from integrability. And what's nice is when we can combine both. Okay. So this is what we are doing. Yeah. So is there any question about what computation we are doing before I go to the why we do this computation? Again, let's keep it as informal as possible. So do ask questions. So this is the computation. We take some gauge, the lightest gauge invariant operator. In n equals 4, there would be this 20 prime BPS operators, dimension 2. There's nothing lightest. We consider 6-point function. We let them approach the cusps of a null hexagon, and then we want to study this object at finite coupling. Okay, so if this is clear, why? There are at least 2 big reasons. One is related to the bootstrap. And it's just the basic observation that if you have n bigger than 4 point functions, this is equivalent to infinitely many 4-point functions, right? Just because you can OP some of the external points and get infinitely many internal points. And we know well how powerful the conformal bootstrap is. Non-abelian conformal. Okay, this is what we are going to do. So we know how powerful the conformal bootstrap is. So for the Ising model, as everyone knows, if you take one 4-point function, you get this beautiful kink. And then you take 2 or 3 4-point functions, and you get this very, very tiny island that determines the theory to huge precision. And that's with 2 or 3 4-point functions. So of course, you would say that if you could include in this business of the conformal bootstrap n bigger than 4-point functions, it has a high promise. It could be very powerful because you are at the same time inputting infinitely many operators. And if already with 2 or 3 you get these amazing islands with that almost look like points, it would be interesting to explore this direction. Now this is hard because n bigger than 5, bigger than 4 involves the geometry is much more complicated, both the kinematics and the dynamics. And this example, where all points are null separated, it's the first entrance into this direction of studying bootstrap with more points. Because when all points are null separated, it's like effectively all points are close to each other. They are not close in Euclidean sense, where the distance is 0 Euclidean, but they are close in the Lorentzian sense, where each distance is close, each point is close to the next point in this Lorentzian sense. So this is a corner where we can actually make analytic progress along the direction of the bootstrap. So here, it's a nice starting point for these higher point explorations, since you have many points that are close to each other. Xi is close from xi plus 1 in this null sense. And so it's quite a lot of points that are becoming close to each other, and that simplifies the analysis a lot. The other point of motivation why we would want to study this is more particular to n equals 4, and I would say it's more related to this open closed string duality. So it so turns out that we start with an n-point function of local operators. So we are starting with closed strings, say, when we describe this 6-point function, for example. Right, so we start with some closed strings. And then at the end, we will get this polygon. And as I will describe, this will be related to a Wilson loop. There will be a relation between correlation functions and Wilson loop. And Wilson loop is described by an open string that stretches here from one point to the other. And in integrability in n equals 4, we know how to describe these Wilson loops in terms of pentagons. So here is a pentagon and the other pentagon. So this business is described in integrability, at least in some kinematics, by pentagons. Correlation functions, in particular, 3 points, 4 points, higher points, is described by this formalism of hexagons. And one thing that we would like to understand is how to bridge both. How to come up with a unified framework that describes open and closed strings at the same time. And this is an important question we would like to understand. So this would be the motivation for doing these explorations. And
but basically, can I precise? So if I know all 4-point correlation functions, in principle, it is already all information. Yeah. So
that's right.
So endpoint does not bring conceptually new information beyond crossing of 4 points.
If I knew all operators.
Yes, if you know all, absolutely all 4 points. Yes.
Right, which is impossible. No one, right? It's too hard. So it's like saying if I know all 3-point functions, and in
the question just theoretical.
All 3-point functions, you also define the theory. But for example, people find it much easier to study a 4-point function and its consistency and obtain immediately infinitely many 3-point functions by this than just analyzing the 3-point functions one by one and making an infinite list.
Yeah.
Similarly here, instead of studying now one 4-point function, we could also take a 5-point function that puts together all 4-point functions at the same time. Or not all, but infinitely many. Okay? And an 8 function would be more or less all, right? Because you can take 2 operators, make an OP, 2 make an OP, 2 make an OP, 2 make an OP, and now with 8, it's like a generating function of everything, right? Right? Yeah, with 5, you can make 2, and then you have 5-point function with 1 leg being special.
Our charge will not, you can't inject our charge, or you can.
The operators have our charge. I mean, one of them can be z squared, the other can be x squared.
Yeah, but in a sense, I mean, you can have lots of derivatives in OP, but our charge won't like grow indefinitely.
Yes. The operators you get in the OP, they have as much total R charge as the 2 OPs that you fuse, yes.
Maybe if I can make another comment, one problem if you try to start from 3-point functions and then reconstruct everything from there is that even if you're just interested in planar things, and all the drawings so far have been planar, then you would have to do non-planar things, and basically you will meet the fact that the large n expansion is not really compatible with the OP. So you're better off sometimes starting with higher point and planar and just staying there if you don't want to deal with non-planarity.
Yeah. Okay, so we are motivated. So now let's do the computation.
Sorry, Pedro.
Yes.
I feel I need to be motivated a bit more.
Okay.
So suppose you could go through this and you calculated some 6-point function precisely and so on. What do you do with this? Why would you want to know this? What's your real motivation?
So what I want in the end, well, one motivation I want in the end is to have a unified description of pentagon and hexagons and understand how they are connected to each other. A side product that I think is likely to come about is a description, for example, of these Wilson loops that will be more versatile than what we have with the pentagons. Right now with the pentagons, we are expanding around one particular kinematical regime, but there are many other kinematics we could want for amplitudes. In particular, we are expanding around the regime where the Wilson loop is very stretched, and that's where the Pentagon decomposition works very well. Now, if we could control these amplitudes coming from a more bootstrap point of view, where crossing symmetry is crucial, it will kind of implement more naturally all the kinematical expansions that you could expand. All channels will be manifestly the same, and you could imagine expanding around any kinematics, and in this way obtain, for example, a formulation of these Wilson loops for any possible kinematics at any coupling. These Wilson loops, I remind you, are dual to scattering amplitudes in the theory. So they would also give you access to all scattering amplitudes at any coupling and any kinematics if this would work. Another motivation is in n equals 4, there are these relations that I'm going to explain between Wilson loops and correlation functions, but often they are wiggly relations. They are kind of schematic relations that in some limit, large spin correlation function should become some Wilson loops and so on. And we wanted to make these dualities precise and obtain really a duality or a triality or a narrow a web of dualities between many observables in n equals 4, like Wilson loops are equivalent to scattering amplitudes that are equivalent to correlation functions. But we wanted to really write sharp equal signs that tell us that in this quantum field theory, this quantity is equal to this quantity. And we are going to do so soon. Okay. Are we motivated now or not yet? Okay. So, but it's great that you're asking lots of questions. It's really lots of fun. Yeah. Okay. So we said what we are going to do, take an n-point function and approach this no limit. We said why. So let's describe the computation. Okay, maybe we could call it how. Okay. So the first thing we want to explore is the geometry of this problem, is to make sure that we take advantage of the fact that we are dealing with a conformal field theory. So things depend on conformal invariant quantities. And we want to take full advantage of that. So let's think of this limit where we take the points to be null. And let's think first, I take point 1 and 2 to be null separated. So 3, 4, 5 and 6 are not yet null. So these guys are going to become null. Okay. Now, when they become null, what happens is that in their OPE, leading twists dominate. That is, when x1 minus x2 squared go to 0, in the channel where I fuse 1 and 2, here I will have the leading twist, the operators with a minimum twist. Twist is dimension minus spin, right? So this would be, what are the leading twist operators in n equals 4? They have twist 2 plus some anomalous twist that depends on the spin. These are operators schematically of the form trace phi s derivatives phi that I would have in any non-abelian conformal gauge theory. Again, some operators with lots of derivatives that describe some kind of folded string. And these operators dominate when points become null separated. So a more familiar perhaps statement is that when points become Euclidean close together, the operators with lowest dimension matter. When they become null separated instead, it's not the lowest dimension, it's the lowest twist. It's dimension minus spin that dominates. Okay, so what is happening is that if I take point 1, 2...
ask here, sorry.
Yeah.
So smallest twist, but the notion of which twist is smallest could change on the coupling, right? Depending on
right. So that's good, a good point. Okay. So this has the smallest twist. This twist is 2 plus some anomalous dimension. But as you are, indeed, if the coupling becomes very big, for example, at some point, this quantity could grow and become even bigger than 4, for example, right? And at some point, when it reaches 4, it could mix with other operators that would now become the leading twist. So they could be operators of the form phi squared times phi squared with derivatives in the middle. So let's suppose we are at a coupling that is finite, but small enough such that they are still the lowest twist operators. Okay, we will get an analytic result and then we can analytically continue for some quantities. But for the derivation, again, because of what Collier said, a physical way of thinking is that we have these operators with large spin, they are the leading twist, but eventually when the spin is big, they are getting lots of rotational energy, so they are becoming heavier, and eventually they could break. And they could break into 2 small operators with just spinning around each other. So it would be like a flux tube that would break. So let's assume that the coupling is finite, but not so big that they could break. So we see that what is happening is the following. So when I take 1, 2 to be null, and then let's also take 3, 4 to be null, and then 5, 6 to be null. And so we are getting this simplified picture where operator 1 and 2 fuse, and I have here leading twist. Let me use this for leading twist. Then I have 3 and 4 that fuse, and I have here leading twist. So let me use this double line for leading twist and single line for the scalars. And then I have 5 and 6 that when they fuse, they give leading twist. So I obtain 3 leading twist operators when I take these points 1, 2, 2, 3, when I take these points to be null. So here, at this stage, we have leading twist and any spin, S. So what is happening is that by taking these points to be null, we are effectively creating some non-local operators, some linear superposition that has any possible spin, 2, 4, 6, 8, any spin matters. So these guys, they are effectively, we are starting to construct a polygon and they are becoming linear combinations of operators that have any possible spin. Okay, so at this point, at step 1, these guys, they have any spin S. Okay. So now let's copy this. And go here. So what we are learning is that if I take this limit where x 1, 2 square, x 3, 4 square, and x 5, 6 square goes to 0, this limit is dominated by 3-point functions, because the interesting part of this correlation function is 3-point function between 3 operators with spin S1, S2, and S3 that are leading twist operators. So it's like leading twist, leading twist, leading twist. And these spins are finite. Okay. So this would be the interesting part. It's the 3-point function that is here. Okay. Now, the second step that we do is we take the remaining points to be null separated. Now, we already have these points be null separated.
Sorry,
we want to
take that spin is finite.
Sorry?
What controls that spin is finite in this case?
It's just the fact that what dominates is the twist. So provided the twist is 2, they all contribute.
Yeah, but spin could be very large. Right?
Yes, it could. By finite, I mean there's no restriction on spin. It can be 2, 4, yeah, anything. Yeah, I should, maybe finite is a bad name. I should say all spins contribute. Now, next, we are going to make this point null separated. We take 4 to be null separated from 5, and we take 1 to be null separated from 6. Okay. So now what happens is that these operators that were delocalized and could have any spin, in particular large spin, what happens is that now they will be dominated by large spin. Because what happens is that these non-local operators, they want to stretch, and they want this endpoint to be null separated from this endpoint so that they emit a fast particle that is absorbed by this particle here. And this point wants to be a finite distance away from point 2 so that it can emit a fast particle that is null separated and propagates here. So what happens in this limit when at the second step I make these new distances to become null, x 3, 4 square, x 5, 6 square, and x 6, 1 square go to 0. What happens is that I'm dominated now by large spin. So this will be dominated by now 3-point function where I have a spin much bigger than 1, a spin much bigger than 1, and a spin much bigger than 1. Okay? And of course, there are the external scalars. But the interesting part here in the middle is now dominated by this 3-point function of very large spin. Okay? So that's what happens that you can see from decomposing this correlation function and then taking these consecutive limits. First, you see right away that when the points become null separated, it's leading twist. And then you see, it's not as trivial, but it's also easy to see that when the points, the other ones are becoming null separated, the sum is dominated by large spin.
In addition to spins, there are also this polarization vectors. Right?
Good. So now, exactly. So as Collier is pointing
excuse me. This
yes.
X, the last one, 6, 1, isn't it 2, 1?
No, 6, 1.
Because you have 3, 4, 5, 6,
3,
and
4,
1.
5, 6. Let's see in the picture.
And then you have to jump.
No. 5, 6 is the wrong one. It's 3, 4, 4, 5. Right? 5, 6 is not what is in the picture, right? In the picture, it's 4, 5, right?
3, 4 is also not the one.
2, 3. Then it should be 2, 3.
2, 3. Yeah. There were several. There were 2 typos. Sorry. Yeah, and then
2, 3.
yeah. Good. Okay, so now we are dominated by a large spin. And as Collier points out, a 3-point function of 3 spinning operators, spinning, doesn't depend only on the spin of the operators, S1, S2, and S3, but it also depends on three integers, L1, L2, and L3, that are related to the polarizations of this operator. So let me explain this. So the point is that when you have a single trace, when you have an operator of the form trace of say Z, and then some derivatives, S derivatives, and then, okay, let me write like this. S derivatives and then Z. This D is what? It's some null direction, so it's some D mu and mu, where this is some null vector. So this tells you in which direction the points are, right? So this would be, when I expand, this direction here would be n of this operator, I call it 2, right? And 2 would be this direction along which they are aligned. And because you have these three vectors, you can make conformal invariants that are related to these polarizations of these vectors. And so the 3-point function now will not be the, or let's write really not the structure constant, but the 3-point function between three spinning operators. So if I write one operator that now depends on a null vector n and the position x, right? And I have j and j, and I have products up to 3 where j runs up to 1 from 3. This is not just some xij to some known powers like we are all used to, but there are also some tensors here, v to the power L1, and then h to the power J1 minus L1, and some other tensors VH, VH. Let me just schematically write one of them so that you get a feeling. But this is just the fact that when you have polarizations, you have more structures you can write. So it is not true that it's just one number times something fixed by conformal symmetry. You can write some conformal invariant tensors using these polarizations. So for example, there are some some H tensors, H. There are, for example, they have two indices, ij, and they could be something like this polarization ni dot nj over 2 times xij square minus ni dot xij times nj dot xij. So that's an example, for example. This is an conformal invariant tensor. There's another one which is v, which has one more index. And then because of this, there are some L's, there are some integers L, and this L, L1, is an integer that runs from 0 to the minimum of J2 and J3. L2 goes up to the minimum of J1 and J3. And similarly, L3 goes up to the minimum of J2 and J1. And so you see that these L's are what they are, and then the correlation function is a sum over these tensor structures that are parameterized by these L's, and each of them therefore comes a structure constant that depends on these L's.
I just discovered I am a chairman and we have a break in 2 minutes.
No.
But we can.
No. It's in 12 minutes.
Mitigate these circumstances.
No, it's in 12 minutes the break.
But we started later. I thought it was 12 minutes, right?
Yeah.
Okay. And so we have these structure constants that depend on L. And so when I said that what this is dominated by large spin and so on, I still have here 3 LJs. It still depends on 3 LJs.
But by the way, what exactly do you mean under the dominate? In this kinematical sense as dependence on coordinates or structure constants dominates? What exactly dominates? It large spins.
Oh, structure constant doesn't depend on whether they are null or not. So it should be dynamical. But how much are suppressed higher twists, Pedro? What is the factor suppressing the higher twist?
Okay, so great question.
Power-like, exponential.
It's so let's describe that. So let's describe that the function, there will be some leading term, and then I'll write the subleading term, and you will see how suppressed it is. Okay, but right now the conclusion, the punchline is that my claim, and now we are going to check that it all seems to work out, is that we have 3 finite at the end. I still have 3 finite LJs, which are related to the possible choices of polarizations or tensor structures. And otherwise, we have 3 spins Sj, which are large, and we are dealing with leading twist. So leading twist is a simplification, large spin is a simplification, and the 3 L's still need to be finite. And the L's are a property of the possible structures of the 3-point function. So the L's are associated to the 3-point function, whereas the statements are associated to the operators, of course. Okay, and all of them are like that. So before we do, let's understand a little bit better how we take these limits in a CFT, because in a CFT, things are functions of cross ratios. They are not just functions of distances, right? So how do we do it? So in practice, let's impose these various limits, but let's describe what are the cross ratios that will describe these limits. So first we took points, remember we took 3 pairs of points to be null, then the other 3 pairs. Okay. So we started with 1 and 2. We wanted 1 to be null from 2. Then there is 3, 4, 5, and 6. And so the idea is let's construct a cross ratio, a ratio of distances that's invariant under conformal transformation that goes to 0 when U1 goes to U2. Okay, so it's easy. We use this distance in the denominator. So I define U1, and then I put immediately the distance x12 square up here. That's the one that's going to go to 0. So this cross ratio is going to go to 0. And then we put other distances. Let's put other distances in another color. They are less important. So for example, to make some distance not null, I could use this distance, for example. So this would be x36 square. And then to make a cross ratio, I divide by these diagonals, this one and this one. So I divide by x13 square, x26 square. All right? So this is definition. Okay, so now taking point 1, 2 to be null, making these points null. Now, as a very sharp mathematical statement, you take the cross ratio U1 and you send U1 to 0. Okay, what about taking the other points to be null? Well, it's very easy. You just define the cross ratios Uj. They are just the same as U1, but you just rotate this definition. So you just replace point x1 xi by xi plus j minus 1, right? You just rotate this definition. So in this way, we get in total 6 cross ratios, right? So we get 6 cross ratios, U1 up to U6, and all of them go to 0, means that I take the various points. U1 goes to 0, this becomes null. U2 goes to 0, this becomes null. U3 to 0, this becomes null. U4 to 0, this becomes null, and so on. So now all of them become 0. Okay? Okay, good. So we start with our correlation function. And the correlation function was a function of these cross ratios, U1 up to U6, and all of them are being sent to 0, and then we are getting a null polygon.
Or could you remind, are they all independent, or like what for 6-point functions, how many cross ratios?
So how many cross ratios do we have for 6-point function? Let's count, and we will see that there are some missing here. That's what's interesting. Very good. So how many are there for 5 points? So for 6 points, let's count quickly. So for 4 points, we can put points in the plane, right? So we put a point at 0, a point at 1, a point at infinity, and then we have a point here at some position z, which has 2 cross ratios, right? The real and imaginary part of z, if you want. Now, this is what you can do in 4 points, right? So for 4 points, we have 2 cross ratios. What about for 5 points? For 5 points, you need to specify 1 more point, right? So you already used conformal symmetry, you have 1 more point. This point now is not in the plane, it's out of the plane in principle, right? So it uses 2 of the directions that are out of the plane. But there is an O2 symmetry that rotates these 2 directions, right? So I can always say that the 5th point is somewhere in the plane, the 5th point. So it is at some point x tilde plus I y tilde. And then it's in the perpendicular direction 3, but it doesn't use direction 4, right? Because I can rotate in 3 and 4 to make it aligned in 3, right? And then there is some component times direction 3, say. And so 5 points has 1, 2, 3 more numbers. So it has 5 cross ratios. And then what about 6 points? Well, 6 points, I have a new point and I already used all the symmetries, so I cannot use anything more. So a new point has 4 more coordinates. So for 6 points, I have 9 cross ratios. And then 7 points, I have a new point, so 4 more, so 13 cross ratios and so on. Right, starting at 4, it jumps by 4. And so we have 9 cross ratios. And here we have 6 cross ratios. And so there are 3 cross ratios that remain that are finite. So these cross ratios, let me call them capital U's, U1, U2, and U3. And these guys are finite. Okay, and this counting matches perfectly. We had said also that we had 3 Lij's that were not yet fixed. And this is related to the fact that when I take the null polygon limit, I take the cross ratios to 0, then I still have 3 cross ratios that parameterize a null polygon. And so this counting is great, that I have here 3, and it's the same 3 that I had over here. So that it had, I needed this freedom, right? Because when I reach a null hexagon, there are 3 finite cross ratios. So let me just, for completeness, tell you what are these cross ratios. So if I make my null polygon, so now all these distances are null. And now we can construct this null polygon, for example, by taking this, right? Now I will use only this distance times this distance. You see, this is finite. I only use finite distances over this distance times this distance. And this picture would be the definition of the cross ratio capital U1. Okay, and then capital U2, Uj, as before, is just a rotation of this picture. Okay, so this is the statement that null polygons, null hexagons have 3 cross ratios. So when you tell me I have a null hexagon, it has 3 parameters that parameterize the null hexagon. Okay. What about null squares and null pentagons? They have no cross ratios. So they are kind of trivial. So if you tell me I have a null square, they're all the same. They're all the same by conformal transformations. I have a null pentagon, they are all the same by conformal transformations. And that's why we started with n equals 6. It's where we start getting something interesting. So n equals 6, there's something interesting. This has a physical counterpart in n equals 4. You probably heard the statement that in n equals 4, 4 and 5 point gluon amplitudes are totally fixed by symmetry. That's precisely because they are described by these null squares and null pentagons that don't have cross ratios. There's no cross ratios I can make with a null pentagon or with a null square. But with a null hexagon, I have 3 cross ratios here. Okay. So now I can answer Collier's question about how are these suppression in leading twist and how do I see? So the point is that my correlation function, let's write now an equation that depends on these u's that go to 0 and on these u's that stay finite. So let me write a formula. So what is this formula? The formula says that, well, first of all, we have to integrate over the spins. So I sum over spin 1, spin 2, and spin 3. I replace the sums by integrals because the spins are very large. So I can replace these sums by integrals. Then what I'm saying is that leading twist dominates. How does it show up? It shows up by having U1. Remember, U1 went to 0. So there will be some U1 here raised to the power of the twist, or it turns out it's half of the twist. So it will be 1 plus gamma of spin. I'm using S for spin. Of spin S1 over 2. This is half the twist of 1. Then there is U3. Remember, U1 was the first one that went to 0, was U1. Then it's you jump twice to get this guy to be null. This is U3 going to 0. And then you jump twice and you go to U5 going to 0. So the odd U's are the ones that dominate the twist. So there is U3 to 1 plus gamma of spin 2 over 2. And then let me continue writing here, U5 to the 1 plus gamma of S3 over 2. I'm going to continue to write the expression, but let me already anticipate that the corrections here, as you now see, would be U1 to the higher twist, and U3 to higher twist, and U5 to higher twist. Okay, so they are exponentially suppressed compared to the leading term, right? I want to finish writing this expression, and then it will be a great point to stop before we continue analyzing it. So my goal is to just finish writing this expression. Okay, so we have this. This is about the dependence on U1, U2, U3. Then what should we dress this expression by? Well, let's go to the picture here. And we see that we have this 3-point function, this 3-point function, this 3-point function, and then the middle one, right? So the external ones and then the internal one. Okay, so that's what we should write. So we should dress this by 3-point function. So there is a 3-point function between one operator with spin and 2 are scalars that depends on spin 1. One operator is spin and the other 2 are scalars that depends on S2. One operator is spin and the other 2 are scalar that depends on S3. And then one where the 3 operators have spin, and this depends on the Sj and on the Lj. Right? Okay, good. Now, then we have to sum over all leading twist operators and its descendants in the limit where what's dominating is the leading twist. So these functions that capture all primaries and descendants are what are called conformal blocks. Once you know the primary, symmetry tells you what the descendants, how the descendants contribute. So now we have a conformal block, but it's important that it's not any conformal block. It's a conformal block for 6 points, which is a harder beast to describe. This guy will depend on the spins, will depend on these L's, will depend, we took leading twist on the cross ratios U2, U4, U6, and on the finite U's, U1, U2, and U3. Okay, and this is just capturing the descendants. You see that the descendants, if you put a derivative, you increase the dimension, but the spin as well. So they contribute as well, right? All these descendants, they also contribute. And this is kinematics. This is just group theory, right? So this is just a conformal group theory. It's a known function. It's the analog of a spherical harmonic, and it's something complicated, but that we know. And so this would be the starting point of our analysis. So, and that's where I will start after the break. We will take this expression and try to see if we can now extract something out of it. And this will be then the starting point for after the break, I think. Okay, maybe to be complete, I should add a sum over the L's here. Yeah, so I think it's a good point to see if there are questions, and we could take over after the break.
Yeah, thank you. So we are back in 10 minutes roughly, but we continue chatting informally with coffee. Andrea, could you stop record, pause recording.
Yeah, Pedro, when you want to start, please.
Okay. Okay, so again, so the conclusion of all this was that we took these points to be null separated, and as Didina was pointing out during the break, we did it by taking first 1, 2 to be null, then 3, 4 to be null, then 5, 6 to be null, and then we take the remaining ones to be null. And the fact that we did it in this particular order leads to the asymmetry, the clear asymmetry of this formula, that the odd U's enter here, and the even U's enter in a completely different way. But of course, the result shouldn't care. I could have rotated and decomposed instead first to 3, then 4, 5, and then 1, 6, and the result has to be the same. And so an important constraint, this would be what is called the Bootstrap-Like Equation, is that this should be the same expression if I just the same, where I just rotate the U's. So the odd and the even, they enter naively in a very non-trivial way, but if I compute this object, it should be invariant under this cyclic transformation, because it doesn't matter how I start decomposing. So that's what we are going to use. So now let's use this equation. Okay, so first, what is the input, the basic input we put is, what do we know about this gamma? So we know that gamma for spin, at large spin, behaves like the so-called cusp anomalous dimension times logarithm of the spin plus the collinear anomalous dimension g of lambda. Okay. So just let me be a bit pedantic and write that this is some sum over n, f n, g to the 2n, g is the coupling, and then plus some g n, okay, g to the 2n, beautiful notation, but okay, I think no one gets confused. And here a log s, right? Okay. Now, what about 3-point functions? So 3-point functions, for example, what do we see in perturbation theory and what do we know? Well, for example, for this guy with one big spin, if I divide by the same object at 3 level, and for simplicity, let me take the log of this object, we know it also has these logs. So it's also a sum from n equal 1 to infinity, g to the 2n, g is the coupling. And then there are also the logs, log of spin. I replace spin by j, sorry. Yeah, if I replace spin by j, okay. Either correct me or don't worry about it. Log of spin, but it's not just a single log. It's not like for the dimension, which is just logarithmic. You can have any power of log where this sum goes up to n. Okay, so you have at most as many logs as the loop order. And therefore, these constants here, c, they depend now on k and n. They have 2 indices here. Okay, and that's if you want a result from perturbation theory, or you could say it's the result of the consistency of these equations that it has to truncate like this. Now, what about the other one? What about the one where you have 3 spinning operators? So for 3 spinning operators, much less is known. And in particular, what we are going to do now to try to make some progress, I will make now a statement about the 3 spinning operator. But the statement that we know how to make over 3 level, let me make the statement when the spin and L are both large. So the spin Sj and Lj are both large. Okay. Then the claim is that this object, or the log of this object, if you want, is also some sum g to the 2n, and then some sum, and now you could have log of S1, but you could also have log of S2, you could also have log of S3, you could also have log of L1, you could have log of L3, and you could have log of L2, right? And what powers Well, to the power k1, to the power k2, to the power k3, to the power k4, to the power k5, to the power k6. And now the constant c depends on this vector k, n, and the summation over all this case is smaller or equal than the loop order n. Okay? And so now the 3-point function would be given at each loop order by a tensor, this big tensor, which parameterizes the various logs. Okay, now here I was summing over all L's, not over large L's. We were summing over large spin because why? Because taking these points to be null, these ones here, said that this summand is dominated by large spin. So we replaced the sums by an integral. And now you could ask, is there a kinematical regime? I have this null hexagon that is parameterized by 3 finite cross ratios. Is there a kinematical corner of these hexagons that also projects into large L?
Sorry about large spin. Could you just clarify this bit? So that the reason for that is because gamma is a little bit negative, right? And it's like growing logarithmically. It depends on the sign, right? Of this.
No, it's because, so you need to recover a singular behavior as U2 goes to 0. And if you keep any finite number of terms, you don't reproduce the singularity. So the singularity really comes from the tail of the sum.
But gamma is also negative or not? I don't remember.
The anomalous dimension is a bit positive, yeah.
Is a bit positive.
Yeah. So it's really that you need to recover a singularity as U2 goes to 0 from a sum of terms that is regular. So the terms are normally, yeah, you need to explore the boundary of the radius of convergence of the sum. Okay, so this guy is going to 0, made the spin large. And now the question is, can I make something on this null hexagon that is parameterized by these guys that will explore on large L? And the answer is yes. And that's a regime that Benjamin, Lance, and Georgios explored recently. That is a so-called origin limit. So this is a particular corner of these null hexagons. And the origin is, as the name indicates, when UI goes to 0. If you have this 3-dimensional UI space, it's the origin, UI goes to 0. And when UI goes to 0, then this sum becomes an integral here over L as well. And this becomes dominated by large L. Things simplify. This conformal block that was a mess becomes just some Basso functions. We can plug these ansatz inside that object and we get Basso functions times logs and powers of logs, and we can do all these integrals. Now we do all these integrals to any loop order, and then we impose that the result is cyclic, and that will give us constraints on this constant C. Right? So these are constrained by cyclicity. Okay. And the claim, and then you ask, okay, how much does it fix of the C's? Right? And the claim is that if you do this exercise for 5 points, I skipped the 5-point exercise, right, for the talk, but we could have done it for 5 points. Then the object that I would be constraining would be 2 operators F spin and 1 is a scalar, right? And then the claim would be that you would fix all these constants at all loops in terms of the constants that appear here in the anomalous dimension. Because we are doing 6 points, we don't fix completely. The result, it will fix most of these constants. Then you plug it into the 6-point function and you get some 6-point function in this limit. Okay, so that's the result I'm going to show. Okay, so again, the exercise was, we start with the decomposition. We impose cyclicity. And this fixes all these constants ck that appear in the 3-point function. And then we plug it back in the decomposition, do those integrals, and we get this. Okay. So this is the claim that this is universal. This is the 6-point function for any conformal gauge theory, how it behaves when the cross ratios, here we call them VI, this VI go to 0, when the VIs goes to 0 and the capital UIs are kept finite. Okay? So now I would like to interpret this solution, this equation, and extract the physics out of this equation, okay? But
Pedro, sorry, can I ask you a question? Can you remind when planarity was used to derive this equation?
So planarity was used when we said that the dimension has logarithmic scaling. This is where we are using planarity.
So it's not true in general that at large spin we have this behavior? I thought it was true.
No, if the spin is much bigger than n, the anomalous dimension at some point will be bigger than 4, like Collie was describing. And the leading twist operators don't have twist 2 plus anomalous dimension, they have twist 4 minus anomalous dimension.
But in perturbative gauge theory, I thought it's true. You think it's not true?
In perturbative gauge theory, well, depends what you call perturbative. Already the word perturbative means that the coupling is much smaller than any combination of spin, right? Because you do perturbation theory, so G is the smallest parameter. But here there was no perturbation theory. I was doing spin was large, coupling a priori is finite. If the coupling is small, then yes, because in perturbation theory you don't break the flux tube. Okay.
Yeah, I'm still not sure. If in perturbative gauge, I mean, if you do perturbative gauge theory, you can ask the question if. Okay, we'll ask later. It's too noisy.
If you do perturbative gauge theory, then the leading twist operators are definitely they have twist 2 for sure. Then this is then in perturbation theory. Yeah, in any perturbative non-abelian gauge theory, this would be okay, yes. Okay, so so this is the final result. So let's digest this formula a bit because it's again, it's not complicated. You have this Basso function to the conformal blocks times logs. You integrate and it produces something, and then you just resum everything and you get this. So this has 3 terms, right? So it has 3 terms as indicated by the 3 lines. So let's see what these are. So there is one term which you see is what we would call the leading divergent part. So this we can call them leading logs. This is just a function of the VIs that go to 0, the cross ratios that go to 0. And it's divergent as the cross ratios go to 0. Then we have some other stuff that is quite local. It only depends on VI and VI plus 1. You see, it's a product up to 6 and it goes around the Wilson loop, a very local structure. And it's also a function of just these VIs that go to 0, that are being sent to 0, but it's a resummation of all of them. And then there is this one, which is a function of the finite UI. Of course, we are in the origin, so these UIs are also taken to be small, but this is now a function of the finite cross ratios. Okay. Here in this sum goes up to these are unfixed polynomials of degree k, and the degree yeah, and there is an upper bound on the degree of the polynomial. Okay, no, it's written here. Yeah, polynomials of degree k. Good. Okay, so do I have 10 minutes to describe then the physics of this formula?
Yes.
Okay. So what is that? So let's now interpret this in light of what would be our physical expectation for this object. And by our, I mean Maldacena, Sokachev, Koshemsky, Aldai, and so on, who proposed the following physical picture. Okay, so this was the result of a rigorous computation in using just Bootstrap. But what is the physical, the picture that we expect? And this is valid in any non-abelian gauge theory. Now, Fernando and Juan and friends propose the following picture. I have these operators that are the lightest operators that are like trace of phi square. And I take them to be null separated. And so when they are null separated, they tell us that they will be dominated, that you see, even at tree level, you can see it, that these propagators that connect them consecutively dominate over the propagators that go in the middle, because those distances are finite. So the physical picture is, I have these points, they are becoming null separated, and because they are becoming null separated, the propagation between these 2 points is becoming classical. And you are generating a fast particle that propagates directly from 1 to 2, then from 2 to 3, then from 3 to 4, and so on. Of course, this particle, this is tree level, but at the quantum level, this particle interacts with, say, the chromodynamic gauge flux tube, say, and starts doing things like this. So what is the picture? What should be the picture? That as the points are becoming null, I generate a fast particle that goes along a polygon interacting with a chromodynamic gauge flux tube. But that's exactly a Wilson loop. That's what a Wilson loop is. A Wilson loop is a classical particle that propagates along a fixed contour, in this case a null polygon, and that interacts with a chromodynamic flux tube. And so the proposal is that the limit, when the points become null, so this should become some kind of Wilson loop. But you see that the devil is in the details, is in these question marks here. So what exactly does this mean? Okay, so let's try to make this a little bit precise. So first of all, and by the way, one reason why this was very interesting was that this Wilson loop then, this polygon Wilson loop, in our case for an hexagon, was related to gluon scattering amplitudes, in this case for 6 gluons. This was because these objects in string theory are related by T-duality. And so by exploring this equal sign, we would have this triangle of relations between correlation functions, Wilson loops, and the scattering amplitudes. Okay, and even more, because as we saw, this is effectively dominated by large spin 3-point functions. So it would be more like a relation between all these objects that would all be related. Higher point functions in no limits are dominated by large spin structure constants. They are related to Wilson loops that are related to scattering amplitudes. And so clarifying these wiggly signs would be clarifying this web of relations, like I said in the beginning. But let's focus on this relation to Wilson loop. A null polygonal Wilson loop is divergent. A null polygonal Wilson loop is divergent because there are all these cusp divergences happening close to the cusp of the Wilson loop. You know that all Wilson loops, they have a divergence proportional to the length of the Wilson loop. And here the length is 0 because it's null. So that divergence is not there, but it has cusps. And so it has these cusp divergences that are governed by the cusp anomalous dimension f of lambda. Scattering amplitudes also have divergences, but they have infrared divergences because we are scattering massless particles. And these divergences of massless particles, they are also governed by the same f of lambda. And this is what governs the light, this light particle scattering. And so these divergences, they are physical. They describe really the fact that if you have a theory of massless particles, you can always hide some particles of very small momenta and you can never see, right? And so these are physical divergences. And where are these physical divergences? They are universal. In any theory, they are predicted in terms of f of lambda and f of lambda. And here we derived that. This is exactly these universal terms that in the first line show up with the precise coefficients as you expect. So if you see these coefficients, this f over 16, f over 8, and g over 4, they are exactly what you predict for how these divergences should behave. What is regulating these divergences here? What regulator are we using? It's the fact that the points are not exactly null. They are approaching a null limit. So we don't start with a null polygon, but we approach a null limit. So the regulator is how close to null they are. And this is how close to 0 this V is, right? And this one, and this one, and this one, and this one. Okay. So this factor here, the name that we should give it is not leading logs. If we want to give it a more physical name, this guy we could call it the Sudakov factor. It's the factor that captures the leading divergences, the physical divergences. They are the so-called in amplitude Sudakov factors or in Wilson loops.
Sir, yeah, could I ask just while you're showing this equation? So a log of V is large, right? And so why
Yes.
don't you expand gamma?
Log of V is large, then it depends on F. If F is small or large, right? If you are doing perturbation theory, F is small, otherwise you could expand.
Yeah, but I mean, if you think about this non-perturbatively, F is finite.
If you take F finite and then the spin to be large, you could expand then this gamma function.
But then
But you could take the limit when you can take the limit. You can take the limit when F times log V is finite. That's even more general, and then you should keep the gamma function.
So it's like weak coupling. But...
That's right. Weak coupling is F times log spin small. Now, strictly speaking, we computed this at weak coupling, but we resummed all loops, right? So now maybe you could take strong coupling, but it's a little bit subtle because as you asked in the beginning, is it true that we know what are the operators with leading twist and there are this level crossing and so on? So let me discuss the gamma function factor next, right? So I was discussing the first line and you are asking questions about the second line. So now let me discuss the second line. So this picture says that when these points become null separated, you form a classical particle. But already in this paper, they said, well, this is a bit dangerous because this particle, it's not really a classical particle. It's a particle that wants to propagate in a null line, but it's a quantum particle. And so this particle, they interact with each other, right? This particle interacts with this particle. They push each other a bit and there could be some back reaction. Instead of going in the trajectory that you want them to go, there could be a recoil effect, right? The particle emits a quantum particle and shifts a little bit its trajectory. And so they said that there could be a recoil effect that you don't get exactly the Wilson loop, but the particle deflects a little bit. So there could be this effect that this will be some, I'm trying to depict here the fact that particles push each other. And then here, there would be a effect that you would call the recoil effect. Okay, this recoil is a subtle business of this back reaction and the fact that particles are not exactly Wilson loops. So they proposed the following equation. They said that the sharp equation they were proposing is the following. Limit when the points go to a null polygon of the correlation function is equal. First, we have the Sudakov factor. That is very sharp and predicted. Sudakov factor for n points. Then you have at some point here in the second line, you have the Wilson loop for n points renormalized once you took out the divergences of the Wilson loop. Right? In our case, this would be a function of u1, u2, u3. This is for n equals 6. For n equals 4 or 5, as I said, there are no Wilson loops. This is just 1. For n equals 7, it's a function of more cross ratios, and for n equals 8, more cross ratios. But then they said this is not a full story. There is here some recoil factor. Well, but then this relation is a bit hard to use, right? Because if you say that plus up to some back reaction, but the back reaction could be complicated, right? So this is the interpretation of this line. This is a prediction to all loops of what this recoil factor should be. So the interpretation is that this factor here is the recoil. Now, they have computed this recoil up to 2 loops in this paper. And if you expand this expression to 2 loops, it matches perfectly with what they predicted. But this is now a prediction for how it generalizes to n loops. And it's this local effect, and you can easily generalize it to any number of points. You just replace 6 by 7, etc. if you want more points.
Sorry, I had some sound problem. So what is the SAN for you? Is it?
Sorry, by this line, I meant the full line. This n is the normalization of the 3-point functions. The 3-point functions are fixed up to an overall normalization. This is just a number. It's just an overall number.
Okay.
It's not important. what's important is the full line. The full line now is an interpretation of this recoil factor.
So can you plot precisely the shape of this classical trajectory now with all these corrections?
No, I don't think, no, I don't know how to translate that in that way. Okay, and then what remains? What remains is a function of finite cross ratios, but okay, then the interpretation is clear. Now the last line is the Wilson loop, the renormalized Wilson loop. Okay, but the Wilson loop, Benjamin and friends had precisely made a prediction based on integrability for how it should behave in this origin limit. Okay. So in the origin limit, okay, so this is what we conclude. So we conclude that this factor is related to...
on the third line, I still have a question about the second one. Pardon, one. So, so you're saying, okay, so this is summation f log v, right? This formula. This is how I should think about it. But then I don't understand this exponent, right? So it looks like if f log v is fixed, then what? Then it will be small, right? So just have one term in this exponent. Am I right? So let's act on like f square log square, then it generates
right.
f
So
square.
if you act on f square log square, you take two derivatives and you get f.
Yeah, and f is small.
Right, f is small. So then if you want, f is small. So this is a resummation in perturbation theory. In perturbation theory, I get any power of logs, and this expression captures them all. Now, in different regimes that you might take, you can drop some terms. For example, there are regimes where you can drop the blue line completely. And again, you just get the first line. But
now, does I don't understand like what is being resounded? Like f log s is being resounded.
So the translation, for example, to this is this here. You understand this c's, right?
Where are you showing? I don't see.
So this constants here.
Yeah.
So we are fixing these constants.
Yeah, but in terms of already a 6-point function, if I look at 6-point function, in which regime this is like the result? That's my question.
Right. So, but let me emphasize here. So here, for example, you could say that you have the high powers of log of spin and you have the smaller powers, right? So what I'm saying is that I capture the leading power of log s, the subleading, the sub-subleading. I capture all powers of log s. What we don't capture are power laws suppressed in S, like 1 over S squared, and so on. That we drop. The analog here is I capture all logs, the leading and not the leading, but then there are power law suppression, exponentially suppressed in U to some power that we don't capture.
So I should think perturbatively about this equation. Otherwise,
yeah, it's better to think perturbatively.
Okay. And then it resums all terms containing any log of v, but not like
yes,
one over.
Exactly that.
Pedro, sorry, a stupid question. What is the partial derivative acting on?
On the gammas. So you just expand the gammas in perturbation theory, like Ollie is saying. So you write 1 plus f log square plus f square log 4 plus dot dot dot.
Variable?
Sorry?
Which variable?
With respect to log v and with respect to log vi plus 1.
Okay.
Which are the variables that appear here, you see. So that would be the recoil, and then this would be the Wilson loop. And this Wilson loop, in general, as I said, it's not known. It is known when one of these cross ratios goes to 0. That's when you stretch the polygon, and then you can write a Pentagon expansion of this Wilson loop to all loops. That's the Pentagon decomposition. And recently it was studied another regime, which is when all the cross ratios go to 0, that's the origin limit. And in the origin, Benjamin and friends had predicted what this object should be. And they predict that this object should be a sum of two functions. So if it's 2, I don't need a sum. It's two functions. One is called a cusp anomalous dimension that's called gamma octagon. That depends on lambda, times log square of some combination of u's, for example, something like that. I'm being schematic, but it's morally speaking correct. Plus another function, gamma hexagon of lambda, times the summation over the other possible logs that could appear, which is log I, log j. Okay. And therefore, what we learn is that actually these polynomials in n equals 4, they truncate, and the maximum power is 2. And not only they truncate, but we know them by comparing with Benjamin and friends, because we know these functions, gamma octagon and gamma hexagon. And therefore, the conclusion is that we learn about the 3-point function of large spin and large polarizations at any value of the coupling in this theory. So in n equals 4 super Young-Mills, by matching with their work, this gives us access to the 3-point function of spin and L large at any value of the coupling. And of course, it would be interesting to now take integrability. And now we have all this data that on the one hand, we could now take hexagons and relate to this object. And Benjamin and friends already took pentagons and related to this object, right? And so we are closing in on the relations we want, which is precisely relations between hexagons and pentagons. And this is, of course, related to the future. That's the kind of things we are working on with, as I said, Carlos, Vasco, and Alexandre. Okay. So I would conclude. So let me mention some open problems. How am I doing on time? I'm very late, actually. Sorry, I need to. Yeah, maybe I will not. I will ask questions. I will answer questions now. We are out of. I think we are running out of time, and I just saw that I'm missing another meeting. I have to send an email saying I'm late. So please ask questions there. And thank you.
Let's thank Pedro.
Yeah.
And now we go to questions. So I didn't quite got this last bit when you like compare with Ben. What happened there?
Just 1 second.
It's a bit imprecise question, I should admit.
Right. So having identified that the last line should correspond to the renormalized Wilson loop, in general, in any theory, we can now use the fact that in n equals 4, we know a lot about these Wilson loops from integrability. In particular, Benjamin and friends noticed a very nice truncation. They noticed that at any value of the coupling, the Wilson loop exponentiates and becomes a simple function given only by 2 functions of the coupling that furthermore they know exactly. They are called the octagon and the hexagon anomalous dimension. And so we can make one more step. So everything so far was totally general, but in n equals 4, this is special to n equals 4. This sum truncates up to power 2. And these polynomials, we know what they are. They are just related to these 2 functions. And because of that, we fix completely this function in n equals 4, which you can translate to saying that you fix completely this function, you fix completely the 3-point function.
But I mean, at large logs, all large logs.
Right, all large logs. So it says that the result exponentiates and you predict the exponent.
So it's analog of
now a nice target to explore from integrability. I take a bunch of particles in the hexagons, right? We sum over all these particles and it should, this hexagonalization should give this sharp prediction. So, right? So this is something we want now to reproduce, understand how this comes about from integrability. So from integrability, now that we have these equal signs here, between these physical quantities here, right? But on the other hand, we have this equality that this is obtained by gluing together some hexagons. 2 hexagons glued together give a 3-point function, a pair of pens. On the other hand, these scattering amplitudes and Wilson loops, they are obtained by gluing together 2 pentagons. And now we want to understand, now that we have sharp equalities between the two, how do I understand this equality directly at finite coupling from integrability? I start with a sum, I start with another sum. How are the two the same? Before it was, I think it was a little bit hard because it was a little bit hard to have a precise equal sign. Right? So the point is that I start with hexagons, I take large spin, and they become pentagons in a way. And that's schematic, but the precise relation, now we have a prediction for what a precise relation should be. Now we should work it out how it works.
So what would be the simplification in terms of this U going to 0 for pentagons or hexagons?
Good question. So it turns out that in this pentagon story, when you sum over pentagon, you are asking from Benjamin's side.
I don't know which side of it is a bit confusing.
You are asking how could people predict this, for example?
No, from 3-point function side.
From 3-point function. No, 3-point function looks complicated. It looks like you have 3 operators, all with lots of spin. It looks like a fun problem. Yeah, it's a challenging problem. I don't know yet.
How U to 0? Do you see any? How does it manifest it? Well, you have to decompose it. Right?
The U's are conjugate variables to the L's. So U to 0 is L's being large.
Yeah.
So L's are related to polarization. So there are some polarizations that are easier than others when you cut and glue operators in 3-point functions. For example, some polarization, it's like all operators are in the same light-like direction. So it's a very SL2 sector-like polarization. Some polarization, they are orthogonal. And so something should simplify when the L's are large.
Mm-hmm. Good, okay, any more questions?
Hi, Pedro. I have a question related to Colliers 1. Which is, so if I understood correctly, you have a more general relationship between large spin structure constant and the full hexagonal Wilson loop.
That's right.
You could also study it at finite U or in the OP limit.
Yes.
So do you expect it to be more tractable, or why do you think that small capital U is going to be simpler to make a relationship?
So small capital U was, I don't know if it's simpler, but historically it was the one we could study, right? So technically it was a little bit easier, but right now, but it's true that a priori we have for, oops, did I lose people? Can you see my screen?
We cannot see the tablet anymore. But...
No, okay, well, let me check. So let me say 2 things. So one is that, so this limit simplifies a little bit because instead of dealing with finite L's, we have large L's, and large L's simplify things a little bit. But in general, it's true we could explore any kinematics. And for example, if we could take all cross ratios U to go to 1, that would correspond to another limit in this 3-point function case that we identified as well, but it's harder to make predictions and to compute. But you are right that a priori, I think it should, that was the hope in the beginning, that we don't need to stick to a particular kinematics. I think geometrically the picture is, in the usual Pentagon decomposition, we do things very sequentially, right? We have one pentagon after the other. Whereas here, we are doing things starting with 3 GKP strings that evolve and we overlap them in the middle in a triangle, right? So it looks more natural that it's an expansion that is more symmetrical. It doesn't have this sequential nature. Now, another thing I could have done is I could have done a more sequential decomposition here. We did what is called a snowflake decomposition because it looks like a snowflake, the picture I'm drawing. But I could have done a different decomposition where I decompose things like this, where now I have a 3-point function here, spin, scalar, scalar, here spin, scalar, scalar, but here I have spin, spin, scalar, and here spin, spin, scalar. Okay. And this should also be another decomposition that should give the same result. And I suspect that this decomposition will be the easiest to make contact with the usual OP. So that would be my guess, that here, this is nice to make contact with the OP limit where U2 goes to 0. This would be the Pentagon OP limit. Whereas the snowflake that we have been discussing today is better to make contact with all cross ratios UI go to 0. This would be the origin limit. But a priori, both would allow you to have access to all kinematics. And,
no, I understand. It's just not clear. I understand what it means to take the spin to be large, the kind of simplification it might bring. Mm-hmm. I'm not quite sure I understand what it means to take the L to be large in terms of simplification, which is something that you are doing to land on this capital U going to 0.
Yes, yes.
And then in the very end, I'm wondering if it is really going to be a shortcut to actually comparing hexagons and pentagons. I would expect, you know, I don't know, if life is simpler, if we are lucky, that possibly there is a more direct way of going from a pentagon to an hexagon, you know, than to actually, you know, reconstruct a full amplitude in a complicated regime and eventually try to reconstruct the matching. But and the OP limit looks simpler in a way because we control the number of particles that are being exchanged and so on.
Right. So the OP limit, for example, in the language that I described of the snowflake, it looks like it corresponds to a limit where one L is much bigger than the other two L's. And in fact, one L is close to, so all L's are large, but two are much smaller than the third one. And the third one is very close to the geometric sum of the spins. So like 1 over L1 is very close to 1 over J1 plus 1 over J3. And L2 and L3, the other L's are much smaller than this L. Now, why does this simplify the 3-point function? I have no idea. So I would have to first understand how to put the L's in the 3-point function, right, of the hexagons. Mm-hmm. But that is not done yet, right? How do I carefully map the computation of the 3-point function where I have the hexagons? I need to put polarizations, contract carefully, decompose and map and see what playing with L's, what simplification does it do on integrability? So that's the 0th order step. That's what we are doing now.
Okay, I have another question if you want.
Sure, yeah.
So I don't know, Volodya is not here, so I feel like obliged to ask what happens in fish chain. Sorry, in fishnet. Shouldn't be confusing.
Naively, I would say that here you put f and g to 0, right? You don't have cusp anomalous dimension or collinear anomalous dimension, right?
Like is there, I mean, there will be some non-trivial term at some point, right? Maybe it's not log S expansion, but something else.
I think it's 1 over S, right? I think it decays. So I think the prediction would be that it becomes a function of this cross ratios capital U of the form of the last line. And naive prediction is first two lines are 1. But
All right, so let's thank Pedro again then.
Thank you.
Then next time, we are having Florian. I don't know if he's around to tell us something about his talk next week. Doesn't look like.
Well, it will be about Youngian symmetry for integrals, for Feynman integrals.
All right. Okay, so see you next week then. One announcement, maybe we'll shift a little bit by 10 minutes because I have some school restriction. I really want to chat informally before it starts, and then I cut the beginning otherwise. And then have to ask questions and delay everyone else. So. All right, thanks everyone. See you next week. Bye-bye.
Thank you. Thanks.
Thanks,
Bye.
Pedro.
Thank you. Bye.
Bye.